Morning, Darcy. Morning, Nguyen. We start class in a few minutes. Okay, good morning, everyone. Shahin is here. This is week 4, and we are going to touch dry friction, and we discuss the start of the friction and when the friction is due to the overcoming the resistive forces in a rigid body, and when the object starts to move with a constant velocity, how the friction changes from static mode to the kinetic mode. So these are the first topic. The second topic is a very important class of structure, which is called truss structure, very applicable into the overhead gantries inside the buildings, bridges, and many important engineering structures. So let's get started. With the friction, I believe everyone has an understanding of the friction from previous subjects, energy and motion. So with that, I try to just summarize. And the only difference here is when we are talking about the friction that is applicable to a rigid body. So a rigid body, in contrast to a particle, it has also capacity to rotate, and that would impact how friction develops, because friction forces does not pass through the center of gravity automatically. If you're talking about the rigid object with physical dimensions like width, height, that rotation would also be impact or influence the development of the friction. All right, so getting started, I mean, the nature of the dry friction, we are not talking about the tribology. This is not a layer of thin lubricating fluid between two objects that is just surface on surface, solid on solid. And the nature of these forces which develop the resistive forces between the object, these are when you try to slide, make a sliding motion, the surfaces are not very smooth and some resistance develop opposite to the direction of the motion. Here in this example, I'm trying to shift that object toward the right and resist the frictions develop opposite to the direction of the motion. But that force is distributed. That's not a single force. It goes over all the interface. It starts from the beginning here and it develops up to here. So yes, that friction force is proportional to how much these two surfaces are pushed together. And that is understandable because why this friction develops, there are asperities, there are rough surfaces, something like the heels, like the sharp edges, they entangle mechanically together. And as a result, the motion becomes difficult. So you only can move when you manage to break that tiny asperities. And once they break, they just they don't disappear. Okay, so that is an exaggerated view of the two surfaces, the blue and gray. They never contact in a flat surface. They contact at the sharp edges, and this is called a mechanical entrapment. So every sharp edges would develop some oblique forces, which can be broken into the normal tangent forces. And all tangent forces added together, we see them as a friction force. All normal forces added together, we see them as a normal reaction force. And that normal is normal to the direction of the sliding. All right, so here in summary, I mean, you already knew about the friction in energy and motion, but the only difference here is when friction develops in a rigid body object, this rigid body is not a zero size particle that has some width and also it has some height, right? And here that force is applied at a certain altitude, not necessarily passing through the center of gravity. And here, just let's see that my driving force P and the resistive force F, they are equal and in opposite directions. So these two forces together, this is the classical definition of the couple. So you remember the definition of the couple. Two forces are equal magnitude in different directions. So that, from translation point of view, they cancel each other. P, F equal size, but that would make a rotational effect in the clockwise direction. So the only way that rotation can be canceled is when your vertical forces making another couple, and this couple should be counterclockwise. The couple due to the normal force and the weight should be in counterclockwise. So these counterclockwise, clockwise, they cancel each other. So not only the horizontal forces or not only the vertical forces sum up to zero, also the net rotation should be zero. That is the difference between a rigid body and a particle. So particle, this is when you lump all the weight inside one single point. It doesn't have any dimension. But rigid body is when that weight is distributed over the object, the force is applied at an offset. So all these offsets, they cause some rotational effect, which eventually they should cancel each other. So this is called the tipping effect. So it means my object tends to tip about this sharp corner. So tipping is that clockwise rotation. It tends to rotate my object to tip over here. And then the weight does a reverse tipping. So that brings that tipping into equilibrium, and the tipping does not take place. All right. So any questions so far before we proceed? Like I said, friction we are summarizing from energy and motion, and the only difference here is we are calculating friction for a rigid body. A rigid body, the friction can cause a tipping effect. So you're pushing a wardrobe, and this not only slides the wardrobe but also tends to rotate the wardrobe for this one to topple. So what stops this from toppling? That's the reverse tipping effect by the weight and normal force. So here you notice weight normal, they have an offset, and driving force, resisting force, they have another offset. So eventually that H and X, they should have a certain relationship such that this object not only is at translational equilibrium, also it is at the rotational equilibrium. So is that clear, the concept to everyone? Do you want me to explain again, or can we go on? Forty, Nguyen, Darcy, is that clear? Can I go on? Thank you, Forty. All right, so now we notice that the friction is also about the material. So we know that metal on ice is smooth, the friction is not that much. If you are rubbing wood against wood, it can develop large frictions. If you are trying to slide leather on wood, that would develop high frictions, relatively medium to high, and or low to medium. And leather on metal, yes, moderate friction. And the highest friction is when you are rubbing aluminum against aluminum. And then why is that? Some people explain this because aluminum sharp edges can weld together at the room temperature. So every time you're overcoming that friction, you're breaking the weldment between the sharp edges, and they weld again. So that is one explanation, is one hypothesis. And here you notice this is the most important diagram for solving the problem in this section. So what this diagram tells me is that diagram is accompanied by a shape. So this shape, I have a block, and then I apply a force of P, and then there is a resist the friction of F. So when the driving force is zero, the friction is zero. When I increase the driving force a little bit, the friction develops. This is a 45 degrees. So it means between this point and that point, my friction force in parallel to the driving force. So whatever the driving force, the friction force. But these two forces, how they are correlated between point. So this is, I call this zone number one. Zone number one. That is a no motion zone. No motion zone. And then this one is a very important point. This is not a zone, that's just a one point. And after this point, that is called motion. That I call this zone number two. If I want to tell you about these three zones, please listen carefully. That simple curve could be difficult to understand. Any force, driving force before that one is force equal to resistance. That is all you can say. Only at this point, I call this onset or beginning of motion. Only at this point, the friction force is equal to mu n. And this mu is a static coefficient of friction. Only at this point. If you move to the second zone, the friction force is mu kn. And mu k is all so smaller than mu S. So it means you need more driving force to overcome the part getting moved, and then the friction become lower. So for every problem you solve, you have to make a judgment whether the problem is in the no motion zone, at the onset of motion, or in the motion mode. If you can make that judgment, you can solve the problem. If you can't make that judgment, simply these formulas only confuses you. You don't know when to use that relationship, when to use that relationship. So this relationship is for zone number one. This relation is for this point, which is the beginning of the motion. And that formula is for the second zone, which is the motion zone. If you can make a judgment for every individual problem, then you are able to solve the problem. Otherwise, you find yourself confused between these three equations. All right, examples. Here, I'm applying a inclined force to the box, and this force is resolved into different components. Some part of this force is being consumed for developing the resistance. So if I break that into two component, horizontal, let me change the color of pen. All right, so this force, I'm breaking that into two forces. That is Px, this one is Py. All right, and making a free body diagram, I have to release this from the surface. So that is the center of gravity. So the weight is exerting here, and I know that the friction is tangent to here, but where should I place the normal force? Should I place my normal force here, or should I place it here or to the left? Which one? Where should I put N? So Nguyen, what should I do? Should I place this at the center or to the right or to the left? Nguyen, Darcy, what do you think? Yeah. Okay, center is not correct, and then I tell you why. Because if I put normal force at the center, then these two forces, they can cancel each other, and then you would produce a rotation by px, and you would create a rotation by py, and these two cannot be contracted. I mean, you have these two forces, px and f, they make a clockwise rotation. So how this clockwise rotation is being canceled? You only can cancel this by a couple, right? So f, px, they're making a couple, clockwise couple. So the only way that couple can be contracted is by another couple. So py cannot make a couple. This is a single force. These two forces, if n is at the center, they cannot produce a rotational effect. So that would that justifies why on this diagram the normal force should have an offset. So offset means my normal force is either to the right or to the left. I can't have normal force at the center. Is that understood, Nguyen? All right, thank you for that. And yes, to begin with, I don't know whether that offset is to the right or left. So don't worry about that. I just make an assumption. I assume that this offset X, whatever that is, I assume this is a positive offset. So, all right, that is 80 Newton times cos 30. And this one is 8 Newton sine 30, which is 40 kilonewton. All right. What is missing here? I did not include the friction force. I call this friction force. And who can tell me whether this is in the first zone, no motion, or this is just beginning of the motion, or this is the motion? Let's read the question. Determine if that remains in equilibrium. Okay, so that means we don't know anything. We don't know whether this is in equilibrium, we don't know whether this is in motion, or we don't know whether this is at onset. It means for now, you have to ignore the coefficient. All you know, in all three cases, which I showed you, one equation is applicable. Whether you are in the first zone, second zone, third zone, the equilibrium of the forces applies. So here I am assuming I don't know whether this is static, onset, or whatever. So horizontal forces, it tells me that the friction force is equal to AT cos 30. These are the only horizontal forces I have. But vertically speaking, I can say that 20 kilogram, which is 20 times 9.8, that minus 20 times 9.8 plus n plus 40 is equal to 0. Or from here, I can work out the normal force, can't I? So this is 30. That is almost, minus 40. Thank you for that, minus 30. So from here, my normal force is nearly 70 Newton. All right. And then how do I find x? To find x, let me take moment of rotation with respect to this point. I call this point S. So if I take net rotation with respect to point S, W doesn't make any rotation, friction force doesn't make any rotation, so the normal force times x, that is a positive rotation, n times x plus, and the other rotation is 80 cos 30 with the arm of rotation of 0.2, and that is a negative rotation, minus 80 cos 30 times 0.2. And then I have a positive rotation due to the 40, that is plus 40, and arm of rotation is 0.4. And that is equal to 0. So from here, I can calculate, because I sub n to here, and that gives me the value of x. If I calculate x, then x is found to be minus 0.009. This is something like 9 millimeter. 9 millimeter. So that negative is telling me, look, your assumption, I assume that the normal is toward the right. It tells me that offset is toward the left. That's okay. We always can rectify the assumption. Just that sign is telling me that. And then more importantly, now I can find out whether this friction force is larger than the onset, because at the onset, the friction force is what? The friction force, if I plot this curve, this is the onset. Only at this point, friction force is equal to mu static multiplied by n. So if I multiply 0.3 by that n times 70, it gives me a force, and then I can compare this force with the real force. The real force, we found this from where? The real force is AT. 80 cos 30. So if you compare them, that is the real force. And if I compare with the force which is needed for the onset, that is 70.8. So this force is smaller than that one. If this is smaller, what does it tell you? It tells you that you are in the no motion regime. So you don't even reach to that point. So this is here. 69.3, that's 69.3. So this point, that is when the friction force becomes 70.8. You haven't reached that. This is the maximum. This is the maximum friction. It only happens at the onset of rotation. Because what you calculated is less than that. It is telling me that this is in a no motion. No motion. So question, if I would have found this force to be equal to that, this was just the beginning of the motion. If my calculation would tell me, for example, the friction force was something like, well, that has two meanings. I mean, even after that, the friction is lower than the maximum. So either I am in the no motion zone or I'm in the static friction mode. Okay, so because we don't have any knowledge regarding the kinetic coefficient, if I knew the kinetic coefficient and by calculating the friction force equal to mu kn and comparing that with this one, that's the only way I can say that's a motion zone, because there is no information regarding the kinetic mode. I can only conclude that this box is in the no motion zone. It doesn't move. The force is not large enough to get this one started. All right. Anyone having difficulty to understand my explanation, just please ask. I'm happy to explain again. Okay, Barnaby, you just joined us now. Let me tell you what you missed. Here, friction force, you are familiar with friction force. There are three zones: no motion or onset of motion when the static friction formula applies, and the kinetic friction, that is when the object is moving. But the difference here, how is this different with your previous understanding? In this subject, Barnaby, we are talking about the rigid object. We are not talking about a particle. So in energy and motion, with the friction, everything was lumped into a particle. This particle doesn't have any dimension. So whether let it be W, let it be N, or let it be friction, everything is lumped at one single point. Here, the forces are distributed. You have a weight acted at the center of gravity. Normal force does not pass through the center of gravity. Friction doesn't pass through here, and driving force doesn't pass through here, generally speaking. So can you see the difference? So as a result of this difference, to find out the forces, you have to solve three conditions that we have: condition of horizontal equilibrium, vertical equilibrium, and rotation. So by applying these conditions, you can find out how much offset is between the normal force and the weight. In the simplified case in energy and motion, you don't have to worry about that. You didn't have to worry about that. Why? Because all forces then, they were passing through the center of gravity. But here, yes, the forces are not concurrent as such. They're making couples, and the only way a couple can be cancelled is by another couple in the opposite direction. So this free body diagram eventually would let you to have two couples which are cancelling, and eventually would make the system rotationally stable. Okay. Who wants me to explain again? Don't be shy. I'm happy to explain this as many times as it needed. All right, if I don't hear any complaint, I assume that everyone is following. That's the only assumption I can make, but feel free anytime if you want me to repeat anything. All right, so let's take 2-3 minutes for everyone to read and try to understand this problem, and then we take it together. 3 minutes starting now. All right, let's get this example together. I start with the free body diagram of the bar, and to make that free body diagram, you have to visualize this object if that has a hypothetical motion. That motion will be um, how this motion would start. Well, the thing is, this particle either is in the no motion zone, part A and B, onset of motion, part A and B, or motion at part A and B. So whatever regime of friction, that would be the same for both points, either that's point A or B, that would be the same. So let's make a two-dimensional view of this one, and that being point A, this one being point B. I know that the weight of this one is being weight of W, that should go right in the middle. And then for point A, the direction of sliding would be horizontal. Therefore, the normal would be like so. I call this NA. But at point B, the sliding will be tangent to the rod. So therefore, the normal at point B is like so. And that I call this NB. And also the friction force is normal to the N. So what do we know at the problem about the zone? If the rod is on the verge of slipping, verge of slipping means this is mu static times NB. That's what it means. And this one is mu S times NA. Okay. So you want to find out the coefficient of the static friction for this to be at the verge of movement. So all you have to do, let's ask ourselves how many unknowns are here. So first of all, W is given. Um, NA is one unknown, NB is two unknown, and mu S is three unknown. So three unknowns, three equation. So you can write the net forces horizontally equal to zero, which is, I mean, you can take your coordinate axis with whatever coordinate system you want. So this will be a 30 degrees. That will be 60 degrees. And this is 30 degrees. You can resolve the forces horizontally, and making vertical no problem. Also, when it comes to point of rotation, you can take the rotation with respect to point A, B, either of them would do the job. So that is being said about the strategy of solving the problem. All right, so this is the detailed solution. You can access this from a slide which is uploaded on Canvas. So in summary, we learned about the friction forces. What is the most important part of this summary is that for a rigid body object, um, you have to consider the offset between how a normal force develops on an object. It doesn't necessarily go through the center of gravity. When you are dealing with a particle, yes, that's true, but with a rigid body, you have to account for the rotational effect. So that brings us to the summary of the friction and the chapter. The next topic, which I'm going to start, that has to do with the truss structure. So what is a truss structure? Anyone knows about the truss structure? Can you tell us where did you see last time a truss structure? So if I go back to the starting slide, here I had a illustration of a truss. So these type of structures, they are very light, they are strong comparing to their weight, and then that makes them very effective. If someone wanted to make a arm like this one of, I don't know, 20 meter, 50 meter, that cannot be made out of the solid material. This is going to be too heavy. And right, so in this case, this is only made of some individual components. And with these individual components, it's very effective in terms of the mass strength ratio. Okay, so this is being used inside the normal structures we call this a beam, but a beam can be composed of the individual links. And the reason for that is to make the structure light and strong at the same time. In some cases, we make a solid beam that those kind of a structure, we deal with them later on. But for now, we just limit ourselves to very simple structures made of the bar structures. So bar structures are simple to analyze. And example of that, you have seen that in the bridges. So this bridge is composed of simple terms. So these simple terms, let me show them to you. So here we have all these individual members. So if you want to disassemble this structure, what you get is a number of links, and these links are connected together with at these points. So how are they connected together? They are connected through what we call as gusset plates. So this is a gusset plate. A gusset plate is used to hold these individual members, and then these are all riveted together. Anyone knows what rivet is? This is the cross section of a rivet, right? So you have two members riveted together. So here we have 6 rivets here, 6 rivets here, and this plate is called gusset plates. So here we still assume that this gusset plate only prevents these members from translational motion. we assume that these are free to rotate, and then ideally that is what we assume a gusset plate is. A gusset plate would let the structure to freely rotate, but from translationally, if you try to pull it or push it, it stays over there. That is very critical to understand a truss structure. So in real life, so that's a photo of the real life. In real life, these are not hinged together. They are being linked with a gusset plate. But in that case, we cannot solve the problem. We only can solve them if we assume that they are being hinged together. And then, yes, it has to be a feasible assumption. It has to be a reasonable assumption. And the reason this assumption is feasible is because the size of the axial load compared to the size of the torque, these are much, much larger than that, the torque. I mean, how much torque does it takes you to break that gusset plate? These are very thin plates. So to break that by the couple is a very small amount of the torque. But to pull this apart, that's a very strong force. So this axial force is significant to that torque. Therefore, it is legitimate to assume that we replace the gusset plate with a pin. Pin prevents this from pulling or pushing. Or if I want to give you a simple way of understanding this, in a truss structure, the members can only become longer or shorter. They never bend. So imagine this bar here. I can initially, that's the bar. If that becomes longer, that becomes longer. If that becomes shorter, it becomes shorter like that, but it never bends. When it bends, the deformed structure of this one. So in truss structure, you never get this one. You either get the member to become shorter or longer. So that is when your member is under tensile load, and this is when your member is under compressive load. That is bending. This is bending. So we assume that bending does not happen in the truss structure. For that reason, why bending doesn't happen? Because all forces can only act at the pin. So there is a force here, there is a force here, but no force between these two. If that ceiling is resting against this bar, it would bend it. So with the truss structure, you can only apply the load at the hinges. You cannot apply between two hinges. Let me explain to you further. So this is a three-dimensional. So for the sake of simplicity, what happens in the back plate is the same as the front plate. All right. So we assume that both of them are the same. But look at the roof structure. Roof structure only connects here, and then there's a gap. Everywhere else there is a gap. It's only roof allowed to sit at these pins. So the roof is not allowed to push against the bar in the middle. It can only push not directly to the bar, but also to the pin. So when it pushes against the pin, what happens? This is the pin. So I'm just showing you that pin here, B. So when you are pushing pin and you are not pushing the bars, pin is acting as a distributor. So that pin would distribute these forces into three forces, right? So pin is acting as a distributor. So that can be seen in the previous figure. So if there are external force at the pin, that external force is distributed between this one, that one, that one. So you are not directly acting this force to the members. You're acting that to the pins, that bolt, and the bolt would distribute this in a elongation mode or shortening mode of each individual members. Is that clear to understand, or do you want me to explain more? Any feedback? All right. So that is all just to define what do we mean by a trust structure. So if you understand this assumption, later on this assumption would help us to solve the problem. So for now, these assumptions, let us summarize them. So I'm summarizing the assumptions. This is a truss structure. When I release the roof from the structure, the external forces at A, B, C, D, they can only act at the hinges. They cannot act between two hinges. And therefore, each individual member can only elongate or shorten. They never can bend. In other words, BC eventually becomes taller or BC eventually becomes shorter. You never get BC to bend like that. If that happens, this is not a truss. The truss, as long as you can manage the forces acting at the pins, yes, the pins are frictionless, and then the members can only become taller or shorter. They never change their radius of curvature. Hopefully, anyone can understand these things. And the other thing is, well, we take a planar view. Planar view means, well, the structure is really 3D, but we can assume that what happens to the front plane is exactly what happens at the back plane. So, in another word, the weight of this structure, you can divide it by half, and only half of that is applied to a two-dimensional structure. So these are the main assumptions you make for solving a truss structure. So let's summarize all the assumptions for what is called a pin joint truss. I deliberately say pin joint truss in contrast with a gusset plate joint truss. So in real life, yes, truss structures are connected through the gusset plate, but that gusset plate resistance toward the rotation is negligible compared to the forces that each individual bar member can take axially or in compression or tension. All right, so this assumption is quite applicable for in general. Let it be a bridge or roof structure. And why do we make an assumption? Because otherwise the members would bend, and then we cannot solve the bend structure in a simple way. A truss structure is simple to solve because all members, the loading are making the parts either becomes longer or become shorter, or they're being loaded axially. They're not loaded transverse to the member. So the weight of a structure is neglected, and if we have to consider them in an analytical sense, we put them as a vertical forces, which are half of the magnitude of force applied at each end of the member. And the member are joined together by frictionless pins. So these are like bearings, like pins, which don't offer any resistance toward the rotation. And that makes sense because each member is supposed to rotate in a simple mode or being elongated or shortened. All right, so that is when you have a bar member in tension, that is the axis of the member. What is the axis of member? You connect from one end to another end, that is the axis. When I say the member is being loaded axially, it means the loads are collinear and they coincide with the axis of the part. Whether they are pulling this apart, which make this one longer, or they are pushing these toward each other, which make this shorter. So either of these two scenarios would happen for every individual member inside a truss structure. A truss structure, you can't have a member changing its radius of curvature. It won't bend. It always becomes longer or shorter. hopefully, I think I repeated that assumptions many times deliberately. Wanted you to just remember that. So two scenarios are possible for every individual constituent of a truss structure. The first scenario is that particular member in tension. The second scenario is that particular member in compression. Tension makes the part longer. Compression makes the part shorter. In neither way, you can have a member changing its radius of curvature. All right, so here, that is a simple pin joint truss. And if I don't include the dotted line member, my structure would be unstable. So if that didn't exist, if that core didn't exist, by applying this force, yes, the member, the parallelogram started to skew, but that is why in most of the building you see that we are making the wooden buildings, and between the frames they are putting something like a cable. So they put cable in both directions. They put the cable here and there in case the loading is that this cable becomes useless and that cable becomes under tension, because cable does not take compression. But if someone is applying a different load, then it could be the case this cable becomes ineffective and the second cable become effective. All right, so all these being said, how do we solve the truss structures? Truss structures are solved in three ways. How do we solve truss? The first is finding the reaction. So finding the reaction, generally that requires a free body diagram for the entire structure. So this is the method, the first method, and you don't need any extra information. From last week, you should be able to make a free body diagram for a truss, find the reaction. And then we did that for a couple of examples, didn't we? That is the first method. The second method, which I'm going to present today for solving a truss, that is the method of joint. Method of joints. So for now, just remember this as MOG. MOG, I'm going to explain to you MOG now. The first one, the first method, we did that last week. We solved some truss structures by finding their reactions. The third method, which we continue next week and the week after that, that is method of section. So method of section, we call this MOS. So today, I go through the method of joint. Also, I solve some example for you to find the reaction of the truss by making a free body diagram of the entire structure. So these two are for today, for the remaining of the class. And then that method, you have to wait until next class. So we go through the method of section. All right, all good. Let's get started. Any question before I move on? Do you want me to go back to something you didn't understand, or you want me to explain again? Please stop me now. Otherwise, I assume that you're ready for method of join. No question, no feedback. All good. I'm used to it. All right, let's start with this first problem. Okay, can I ask everyone to spend 5 minutes, and in 5 minutes, I want you to find the forces in each individual member. Okay? 5 minutes to think, and after that, we discuss it all together, and hopefully we solve it together. Your 5 minutes start now. Okay, everyone, let's take this question together. This is the most simple truss structure you can imagine. And the reason this is simple is because it only has got how many members? It has 1, 2, 3 members, right? So this is the most simple truss. I mean, you could have something with more joints. I mean, the next one would be something like that. Okay, imagine that is a truss structure. And how many members this one has? A, B, C, D. So one member here, two members, three members, 4, 5. This one has 5 members, but the one which we are solving, this only has 3 members. So how do I go with solving this problem? Let's make method of nodes or method of joint or MOG. We want to do method of joint. So method of joint, how does it work? You make a enclosure. This is an enclosure. And this enclosure is cutting my structure through BA. It's cutting my structure through BC. Can you see that? So if I do this, what's going to happen? Let's see. I'm making my free body diagram cutting through BA through BC. And in that, I have to include the external force, which is 500 Newton. And then, because I'm cutting these two members, the internal forces, after cutting, they become exposed. This is like you are cutting a hose which has water in it, and then the water comes off. So you have to include the internal forces inside BA, internal force inside BC. And these forces, we don't know whether they are tensile or compressive, but we do know that they are going to be axial. They can only be axial to the member. All right. How do I label them? The labeling of the forces are very important when you are solving a truss structure. So you label the nodes, and the forces are being labeled by the letters going from the beginning to the end. So here when I cut that, I'm cutting BA. I go from B to A, so I call this FBA. What should I call this one? The second one. Porty, what should I label the force inside BC? What should I label this one, Porty? Nguyen, what should I label this second force going from B to C? Barnaby, what should I call this force? Let's call this FBC. Yes, thank you for that. Thank you, Nguyen, FBC. Now, this pre-bio diagram, how many unknowns does it have? Yes, it has 2 unknowns. Thank you, Porty. So we should be able to solve that, shouldn't we? It's only 2 forces. But let me tell you that this is one solution approach. Here, 1 unknown here, 2 unknown here. And how many equations, Porty, how many equations I have for this pre-bio diagram? Do I have 3 equations or 2 equations? Why 2 equations? Why not 3 equations? Because generally speaking, we have one condition for X translation, one equation for Y translation, and one equation for rotation. Why are you saying 2? Why not 3? Are you still sure this is 2? Yes, Porty, your answer is correct. But if you can explain to me why we only have 2 equations and not 3 equations, I'm happy to give you 1 bonus mark for the mid-semester exam. Anyone can explain why we can only have two equations here, not equations? I would give them 1 bonus mark for the exam. Barnaby, Daniel, okay. The exit, well, that, no, my question, Nguyen, my question is generally, thank you, Porty. Thank you, Porty. Porty is right. You get 1 bonus mark for the exam. Porty, remind me when I'm giving your mid-semester exams question, I give you 1 bonus mark. Anyone can elaborate. So Porty's answer is correct. Anyone can elaborate why we only have 2 equations and not 3 conditions. Feel free to explain, Barnaby, Daniel, Darcy, Nguyen. You still have chance. If you answer the question elaborating or explaining, you get 1 bonus mark for that. All right, so let's say it this way. We are trying to apply the rotation equation. According to Porty, there is no rotation about B. Let us investigate what the big scientist Porty told us. That is, Porty is telling me that if I take rotation about point M, that would give me no new information. So starting with 500, what rotation 500 makes? So let's wait for Barnaby to come back again. He has a poor internet connection, right? Barnaby, can you hear me well? Can you see the screen well? All right. Nguyen is telling me that for 500 with respect to point B, that's counterclockwise. Is he right or? So let's see. 500 is passing through point B. So the rotation due to that is 500 times 0. So that is 0. 0 rotation due to 500. What is the rotation of FBC with respect to the B? That is plus or minus, doesn't matter. That is FBC multiplied by arm of rotation. It's passing through B, that is times 0. And what about FBA? That is plus or minus, doesn't matter. FBA multiplied by arm of rotation. That is passing through B, that is 0. Okay? So I have to set this equal to 0. That gives me 0 is equal to 0. That I started from this condition. And that condition is telling me something nonsense. Why this is nonsense? Because I know 0 is equal to 0. I don't need to go through all these calculations to find out that 0 is equal to 0. All right, I hope everyone is one step closer to what Porty anticipated. So Porty acted like this was a prophecy of Porty. He just told us at the onset that the rotation is not a useful equation in this case. And now I want to make a general conclusion. Please listen carefully, everyone. Do you remember when I told you about the system of forces which are concurrent? Who can tell me, who can remind me what a concurrent system of forces are? Barnaby, is this a concurrent force system or it is non-concurrent? Daniel, Darcy, Nguyen, is this concurrent or non-concurrent, the system of forces in my free body diagram? Are these forces all colliding at one single point? Yes? No? All right. So therefore, Nguyen, that is my conclusion. If in a free body diagram, all forces are colliding at one single force, this free body diagram only has 2 useful equations, not 3 useful equations. Because the third useful equation, this is net rotation, that doesn't give me any information. So let me recap my conclusion. This is so important. I'm gonna type this out for you. Just let me type this one for everyone. Okay. How is this conclusion? Who agrees with this conclusion? So here I have a free body diagram. In this free body diagram, the forces, all forces are colliding at one single point, or the system of forces are concurrent. When the system of forces are concurrent or colliding at one single point, you only have two useful equations. You don't have three useful conditions. Okay, so that the conclusion is method of joint. In every joint, the forces are concurrent. If I make a free body diagram for C, for example, if I make a method of joint about point C, this is method of joint applied to C. So how my free body diagram looks like? Let's draw this together. At point C, I am cutting through BC, I'm cutting through AC. So that would make one force of CB here, a force of CA here, and also reaction, I have a force of CY. So that is point C. So this free body diagram, is this concurrent or is this non-concurrent? Darcy, Daniel, Barnaby, Nguyen. Can you say that this free body diagram only has two useful? It is concurrent. Why none? Because all forces are colliding at C. All forces are colliding at C. So if I write net rotation with respect to the C equal to 0, the result is 0 equal to 0. Nonsense. That is not useful. Everyone agrees with that? Just bear me for a second. I have to take this call. It's from my doctor. Just bear me. Sorry, everyone. I'll be with you in 5 minutes. I'm just taking call from my doctor. I'll be back in 2 minutes. Thank you. Okay, sorry about that, guys. I had to take that call from my doctor, and now we're back to the business. So here I made a free body diagram of method of joint. I call this method of joint at C. So let's call this method of joint or MOG at C. So this is MOG at C. What about this one? This one is method of joint at B. So method of joint at B. And again, I noticed that method of joint at C, the forces are concurrent. When the forces are concurrent, the rotation does not give me any meaningful information. So what if I apply the method of joint at A? Anyone can help me to apply method of joint at A. So if I apply method of joint at A, what happens? I have to release that reaction. That would require two forces, one force AX, one force AY, and then I have another force MAB, and also I have another force MAC. So this is FAC, this is FAB, and this one is a reaction force horizontal, and this is reaction force vertical. And that is method of joint applied at A. So if I apply method of joint at A, that is the free body diagram I get. So who can tell me if this free body diagram, is this a concurrent or this is non-concurrent? Nguyen, is this concurrent or non-concurrent? Are these forces all passing through a single point or not? They are passing through a single point. Well done, Nguyen. And what it means is, if I apply the condition of rotation, the condition of rotation tells me 0 is equal to 0. That is not useful. Okay? So the big conclusion I want to make from this problem for everyone is, whenever you apply method of joint, no matter which joint or every joint, this is the limitation of method of joint. Method of joint, whenever you apply it, the free body diagram becomes concurrent. And when it is concurrent, you only have two useful conditions. And that means method of joint can only handle two unknowns. If the joint has three unknowns, the method of joint is useless. All right? So you can't use method of joint when there are more than two unknowns. In this case, yes, I can solve method of joint at B because it has 1, 2. I can solve it. Can I solve method of joint at C? Yes or no? Anyone can tell me if method of joint at C is applicable or not. If they can explain, 1 bonus mark for the mid-semester test. Anyone can tell me if method of joint is applicable at C or is not applicable at C, and they can explain why. Forty, can you explain? Nguyen, Barnaby. So if I apply method of joint at C, how many unknowns do I get? When I apply it at C, I don't know what CY is. So this is one unknown here. I don't know what FBC is. That's two unknown. I don't know FCA. That's three unknown. Three unknowns. That is not solvable, because method of joint at C can only handle two unknowns because the forces are concurrent. So what should I do? I mean, few things I can do. I can't use method of joint at A because it has 1, 2, 3, 4 unknowns here. And method of joint can only handle two unknowns at a time. All right? So my conclusion is To start with, I can start with method of join at B, but I cannot start it at C. Maybe I can postpone use of method of join at C after I solve for B, and then that is doable. Why is doable? Because let me explain that to everyone. Just bear with me. So for the very same problem, okay, for the very same problem, here what I needed a strategy. So my strategy is I start method of joint at C? Yes or no? No, we can't. Well done, Nguyen. Can I start method of joint at A? Yes or no? No. Thank you, Nguyen. Can I start method of joint at B? Yes. Well done. Well done, Nguyen. So here, this is all decision. It is up to you whether you want to start it at A, B, C. But if you decide to start it at A, you will be disappointed because that's not solvable. If you decide to start method of joint at C, you will be disappointed. This is not solvable. But if you solve it at B, you can solve it. And then more importantly, let me draw the free body diagram for BC. If I choose BC, that is free body diagram for BC. This is FBA and this is FAB. Can I assume that FBA is equal to FAB? Yes or no? Well, that's not difficult, is it? Just take a x-axis parallel to this one, and then if you write net forces along the x equal to 0, what you get is the force at one end is equal to the force at the other end. Can you see that? Any feedback? Yes, no? Just I'm in limbo. Let me know. All right, thank you for that. So here, that is my conclusion. When I apply method of join at B, what I find here, that is FBA. But the very same force, I can transfer this one to this one. That is FCA, CB. This is BC, this is CB. So if I decide to solve the method of joint at point B, if I apply method of joint at B, what I find is FBC. All right, that is my first step. In the second step, I want to apply method of joint at C, but this time my free body diagram does not have three unknowns. My free body diagram has FCA, it has C of Y, but the third force is not unknown. The third force is equal to, this is FCB is equal to FBC. So when I finish with that one, FBC, I know the value. I bring that to this second free body diagram. Now, how many unknowns are here? 1, 2. Is this solvable now at this stage? As a second stage, can I apply method of joint at C? Can I or can't I? Yes, well done, Nguyen. So all I want is for everyone to understand why did we postpone solution of C? If we just got the method of joint at C as a first step, that was not solvable. But if you solve step 1 method of joint at B, then whatever answer you get, you can transfer this to the second step. The second step is method of joint at C, and then you reduce the number of unknown from 3 to 2. Now your 3-way diagram only has 2. Now imagine now I did step 1 method of joint at B, stage 2 method of joint at C, and the third step I want to do the method of joint at A. Let's see what happens. If I apply that, my 3-way diagram would look like this one. This will be FAC, that would be FAB, and this is AX, this is AY. So how many unknowns here? That FBA, I should know that, because here, after solving the first step, I not only get FBC, but also I get FBA, right? But FBA is equal to FAB. So here, FAB is a non-value. In the second step, what I get is FCA. FCA can be calculated in the second step, and FCA is equal to FAC. So FAC from the second step, I plus it here. So this is known, this is known. Only unknown is AY, AX. So one unknown, two unknown. And this is method of joint. Method of joint can handle 2. But then the condition is you have to postpone choosing this method of joint. You can't do it in any order you want. You have to follow a very specific order. The order that we choose here is first we start method of joint at B. Second, we apply method of joint at C. Third, we apply method of joint at A. Anyone can agree with that strategy? Can you see why did we choose that sequence? Yes? No? Don't be shy. If you don't understand, please ask. I'm happy to explain again. Hello? Yes? No? Any? Okay, thank you, Porty. What about Nguyen? What about Daniel? What about Barnaby? Just don't be shy. If you want me to explain again, I would explain it as many times as it takes. Thank you, Nguyen. All right, now that being said, I just want to tell you another way. We know that problems can have different solutions. So if I specifically tell you that, look, I want you to solve this problem by method of joint, you have to do it, as I said, first method of joint at B, then second step method of joint at C, and third step method of joint at A. But if I don't tell you, if I don't specify method of joint, is there another way of solving this problem? All right, your internet is not good, is it? Barnaby, try to limit the number of browser tabs you have. If you have multiple browsers, maybe they would reduce the speed of internet. Yeah, just keep one tab active. Just kill any other one. Maybe that would help. By the way, Barnaby, all these are being recorded. If you having difficulty now, you can watch them on YouTube. YouTube, you get a quality recording there. Okay? Please make sure you watch them on YouTube. Will you? I already sent you, I already sent you the link. That was my last announcement. That channel, I'm dedicating that channel for recorded sessions. I mean, in the Collaborate Ultra, sometimes it's not easy to stream the videos, but on YouTube, you can even watch them on a mobile phone with a low bandwidth. All right, let's go on. My question, let's go back to my question. If I don't ask you specifically to do this with method of joint, is there any other way you can solve this problem? The answer is yes. And in this case, I want to take not method of joint. I want to take the entire structure. I want to release that from A. I want to release that from C. Can you help me to solve problem like that? All right. So I'm releasing the entire structure. That is the method one. I told you with the truss structure, there are three methods. With the truss structure, there are three methods. The method one was the entire structure. Method two was method of joint. The third method was method of section. Method of section, I tell you about that tomorrow, but method of joint, you know that now. Method of entire structure, I do it right now. Let's solve this problem by taking the entire structure. Entire structure, I would take it like so. Because I release A would resist in the X direction, Y direction. And how about C? C is a roller support. It has one here, and then I have one force here. So that is 500 Newton here, and AX here, AY here, and CY here. So this problem, this free body diagram, this has, how many unknowns does it have? Nguyen, how many unknowns are here? 3. Is this solvable or not, Nguyen? Yes, well done. And the reason here you can solve 3 is because the forces are not colliding at one single. So this is a non-concurrent. Non-concurrent. So here the forces do not collide at one single point. So in another word, this system has the capacity to rotate. When I do the method of joint, this free body diagram does not have capacity to rotate. It gives me 0 equal to 0. But here, if I write the condition of rotation, I never get 0 equal to 0. So here I have 3 useful conditions, 3 unknowns. With the method of joint, I have 2 useful conditions and only can handle 2 unknowns. Is that clear? So this problem is solvable. How do I solve this problem? I would apply net forces horizontally equal to 0. That give me AX equal to minus 500. And then I apply net forces vertically equal to 0. And then I apply net rotation with respect to point A equal to 0, which gives me CY. And this CY, I bring that to this equation, and that gives me AY. All right, so that is the method of entire structure. And I have the full solution of this problem included in the slide. So instead of going through the numbers for you, I decided to tell you about the strategy. So that is when you do the method of joint at B, you only have 2 unknowns. That is solvable. Then you go to the method of joint at C. If you go to the method of joint at C, that has only 2 unknowns because you already know that force from the previous step solution, and that is solvable. And finally, you can do method of joint at A because you already know the magnitude of FCA, FBA, and this has only 2 unknowns. Alternatively, if you want to do the entire structure, the entire structure has 3 unknowns, 3 conditions, which is easily solvable. So let's summarize. How do we do method of joint in general? The method of joint, you make a free body diagram for the complete truss. So that is the entire truss. The entire truss free body diagram is useful to give you the reactions at the supports. And not always you need to know the support. Let's go back to the previous example. In the previous example, if I ask you what are the forces in BA, BC, you don't need to solve the entire structure. Simply by one step, doing the method of joint at B, that is enough to give you the forces in BC and BA. For that, you don't need to know the reaction at A, you don't need to know reaction at C. Does that make sense? So not always you are interested to find the reaction. Only if the problem insists, if the in the exam I specifically tell you, look, find out the forces in each individual member, then you don't have to solve the entire structure. But now, that being said, this could be a thing we can do. And then make sure you label all the joints using the uppercase letter from A to Z. Don't include I and O. I and O could be confusing. And then at each label, include the external support reactions, external forces, and then you have to decide what is the order you want to solve. You have to choose the right method of joint. Otherwise, if you started from the wrong place, that is not solvable. So you find the forces you find, you can transfer them to the next step. All right? So what you find from one step can be transferred to another step, make the next step solvable. And this problem, that is, you want to find the forces. And how do we do that? If I want to find the reactions, what I do is I release the entire structure. The entire structure would give me two unknowns here, one unknown here. So 1, 2, 3. This 3-by diagram is solvable. So once I solve that, at point C, I would only have two unknowns. So if I apply method of joint at C, I would get only two unknowns, this one being found from the previous stage. So this one is known, this is one unknown, two unknown, and method of joint can handle two unknowns. So that gives me the internal forces here. The next step, I can apply method of joint at B, because at that stage, I know the forces here, and that only has one unknown here, one unknown over there. That is solvable. And then I can go on method of joint applied at D, because these two are given, and only this one to be checked. And finally, with all of these, you can apply method of joint at A. So today, you have the detailed solution for this. I encourage you to go and watch the entire solution from the slide. So tomorrow, we go through the remaining of this method of joint. And two important classification I have to tell you tomorrow, that are some structure, just by looking at them, we can identify some members are redundant. So for example, in this structure, this member is redundant, this member is redundant. Why? I tell you tomorrow. So in this structure, there are few redundant members. So this is redundant, that is redundant. And yes, this means this is redundant, that is redundant. So 4 members can be removed, and you only have to solve this structure. So that is called zero force member, or ZFM. So zero force members, remind me tomorrow to explain that to the class. So for now, all you need to know is some structures, they have members which are redundant. You can get rid of them. And by removing, it makes the solution simpler, but it's a valid solution. You can make a valid solution of that. Okay, so now let me finish the attendance for today. And if there is any question, so Serish away, Natasha away, Nguyen is here, Aiden away, Chaisal away, Daniel was here, and Abdullah away, Jonathan gone, Ahmed gone, Nijil away, Barnaby in, and Flynn away, Shaw away, Darcy in, and Porty in. Okay, any question? Thank you very much for being patient, audience. I look forward to see you tomorrow, 8:30 to 10:30 in TC. All right. Thank you, Arnaby. Thank you, Daniel. Thank you, Noyan. Thank you, Corti. See you tomorrow. Bye. Thank you, Daniel. See you.